Yes, my head is full now with a lot of ideas, and I'm happy to hear so many different ideas from many fields. So that's what I like to connect ideas, and I will present you now something completely different. There would be a lot of things to tell, but I thought to concentrate on just one small topic. This is the basic elements of informations as I see them. I have been programmer for about 40 years, so information is something that interests me a lot. And information has also algorithms, and algorithms has to do with logic. And if you are interested in logic, you come very soon to paradoxes. And paradoxes and Spencer Brown has to do together a lot. And another point with the paradoxes and chapter 11 is the frequencies. And frequencies and resonances as a musician interest me. But I will not talk about this. I will just talk about now about the two most basic elements of information as I see them. One is the bit, very famous, and the other one is the distinction, here also very famous. Yeah. So the question is, what do they have in common, and what are the differences, and can we shape one with the other? For the last question, my answer is no. And I will answer you the question what they have in common and what they have as a difference. Common is going from 1 to 2, because both the distinction and the bit are an action. They have a moving from a distinction is to draw a distinction is a move. And if you choose one side of the bit, it is also a choice. And the action goes to a state, and the state are possible outcomes. The possible outcomes of the bit is not clear, because it can be 0 or 1, true or false, or anything else, just 2. And the bit says just which one is indicated, but it does not say what it means. And of course, meaning is important for information. Now, this is different for distinction. We have inside and outside. And I come to the differences. To come to the differences, I will talk about the bit, because I think I will not talk about the distinction, because it's not up to me to talk about this. So you know much better. But I will talk about the bit. The bit is a really new concept, because it stems from 1948, when an engineer of a telephone company tried to calculate the flow, the electric flow in the cables. And he invented the name bit as binary digit. It is a joke too, because bit means a little bit, but it's an abbreviation. And it talks about signals, not about meaning. And one bit is a selection of 2 equiprobable states. And the bits, they measure the information content as entropy. Entropy, I think it was not discussed in this conference yet, but what is entropy? Entropy is very important for information. Entropy also is a relatively new concept. It stems from the 19th century, and it was connected by Shannon as information entropy. It comes from thermodynamics, the notion of entropy. And bit is, the information entropy is much more general than the thermodynamic entropy. We have in physics, there are two general laws, the first and the second law of thermodynamics. But they are general laws. They are not, they don't apply only to thermodynamics, but they apply throughout physics. I hope the physicians here will not, I don't have to be ashamed of the physician, in front of the physicians to say that. But the first law of thermodynamics is an equation. And the second law is an unequation. Here, the formulas mean dE is the energy and S is the entropy. And they both talk about the flow of that during time. dt means time. So which change happens with energy in time in a closed system. And the first law says there is no change. But for the entropy, the second law says there can be a change. And most times it is a change. And the flow is always greater than zero. All the calculations in physics, like Newton's or Schrödinger, they are calculations with this equation. Actually, this equation. So if you look at the Schrödinger equation, it is dE, it is just this one. What means now entropy? Entropy is a word that most people don't like because it's not so easy to understand. Many people think it means chaos or disorder, but it's not true. It can mean disorder, but it can also help to bring order. And what I liked especially is this presentation of the last conference by so many names. My head is a little bit confused. How we call the first or the architect. Andrew, yeah. Andrew had a fantastic visualization of all this. Yeah. So, but I will not bring it here. So I will just answer the question, what means entropy? There is an example of Psalm where to explain that. So where is my key is the example of a school teacher who has lost his key in the schoolhouse. In which floor? There are two floors. So it is just a decision or an information or an entropy of a decision of 2. A decision of 2 is 1 bit. So bit, this is the formula for the bit. It says that if you have a choice of 2, you go always with a logarithm of the objects, the possible outcomes, to the base of 2. That is the bit. So if you have a base, you have a choice of 2, like 2 floors, it is 1 bit. This is not enough. He doesn't know where the key is. He just knows which floor. So if he wants to know about the floor, more about the floor, the key, there are maybe four rooms. So in which room is it? So we have 4 choices, and this means 2 bits, logarithmically. Yeah, I should more tell about this. So you cannot, even if he knows in which room it is, maybe he doesn't find the key. So you can always go further in details. Yeah, it looks like the unmarked state, doesn't it? Okay, about the entropy. There's 2 levels that define the entropy. So if you look at these 2 levels, you have 1 bit. If you look at the level where you know nothing and then you know which floor, you have 3 bits, yeah? 2 and 1. So bits and entropy are relative. You cannot say there is an absolute measure of the information somewhere. So you can always have more details and more information. So you have to look for which level you talk. If you talk in a fine grade level, it's called micro level. There is some theories about this, a lot of theories, like Weizsäcker and many other about these levels. And bit, by definition, today is the difference between the two levels. So in one level, you know the details, and in the micro level, you know the details, and in the macro level, you do not know them. And this defines the bit. And this defines the entropy too. So you cannot say it's disorder or order, it's just the difference between these two. Once you know it and once you do not know. So we can say the information in entropy is like a tension between these two levels. Or you can also say it is a surprise when I come to know where the key is. You can also say you move from intransparency to transparency. Transparency, but the transparency is not here. Yeah. Okay. So we have to move. So the entropy is something very dynamic because it's moving. And when we think and when we live, our mind moves always from the overview to the details and from the details to the overview. My job was to do classifications with natural language processing. It has nothing to do with the neural networks. It was another method. It was an explicit method to do that. And we had to interpret the medical language of the physicians and to code them. Now, coding means classification. And a classification is always a simplification. It is an interpretation of what really is meant, and it is a simplification. It gives you an overview. It gives you a clarity. Okay. Okay. So we can move from the macro level to the micro level and back. Because I know here, I could have any signals here from the reality. It's just a question, how do I interpret them? And interpretation is a bidirectional thing. So the expectation of which signals I look at, this is coming from the interpreter. So it is the expectation and the input from outside that move together and have an interesting interplay. So we try to formalize this interplay, and that's what we did. The thing about the macro level is there are different macro levels with the same signals, because you make a simplification, a selection of the signals. It depends which signals you look at. So depending on this, you can come to different interpretation. That's what we experience. Everybody of us interprets the reality differently. It's just a fact. But we try also to adjust or to bring together or bring in resonance our interpretations. That is, I think, one of the reasons why we are here, not only here in this room, but also in the world. Language has to do also with these interpretations, because language is a slippery thing. So there is a lot of misunderstanding in words. And this was is best shown with the semiotic triangle. the semiotic triangle has a very, very long history. Aristotle and many others, Peirce, Piaget, I know it from Sova, Ogden Richards formalized this very fine. They say there is a triangle, the semiotic triangle, that is two-sided. Usually people think a book, the word, is the thing, the object. But that's not true. Because if I say the book, you look here, you see one book. I mean this book now, it's a word book. But I could also mean this one or this one. And there are a lot of misunderstandings with words. If you think a word has just one object. And how are they related? They are related with the concept. And the concept is something in our heads. So if I do not have a concept for a Chinese, if I have a Chinese word, I don't know, but maybe I have the concept. I can make this link. But if I do not have a concept, the words do not help me. They don't mean anything. So I must beforehand, I must have a concept in my head. There's also the constructivists, you all know them, like Bateson and many others. They say we put these concepts in our heads. And in our heads, that's the next slide. First I show this one. We have here visualization of reality and interpreter. The interpretive system, that's also a book I propagate. I wrote this 20 years ago in German. Now this is the English version. And here you see also the work of entropy, because you see here many signals, and here is the interpretation. That's the visualization of the entropy. Exactly. Who draws the distinction? That's a question. And I think it is just the human mind that makes the interpretation, that draws the distinction. So we have EIS it has nothing to do with the terrorist group. I coined this abbreviation before. So the interpretive system is the one who looks at reality and makes the macrostate in his head. And he reconstructs what he sees. If I see now this room, it is just a reconstruction in my head. At the same time, the room really exists. So if I would not believe this, I would be a solipsist. I'm not. Yeah. So the interpretation reconstructs the reality. Of course, it's a simplification. It's not a full reality. You can also write this in forms. So you see the full reality is, if you see the interpretive system, you can distinguish it from the full reality. It's a part. And the interpretive system, it reconstructs what it sees outside. But nobody's alone. I could not talk to you if I would not have known language from the childhood. And later English, yeah, but it's not my language. But but I'm not alone, and we could not communicate if we were alone. And you see here the triangles of two interpreters. They both reconstruct their reality in the full reality. But they do not see the full reality. Nobody of us does it. We just have objected parts of reality. And there is a common part where the two players, they can talk because they know the words and they see the objects. So they have a common reality, at a common observed reality. And there must be a resonance between these pictures in the heads. If there is no resonance, it will not work. The question is, how does the resonance come into existence? How does it evolve? That's a big question. I don't go into details now, but there is an interesting play between these two players who adjust the meaning of the words. And this is a dynamic process, and it's going on and going on. It's not a static process. It's really a dynamic process. I come now closer to the end. Common for the distinction, as I told, is the choice of the bit, choice of true. And the distinction is also an action. And both actions can have outcomes just two, because they are very, very basic. Just one action and two outcomes, possible outcomes. Yeah. So we have one basic information step from 1 to 2, from macro to micro, because the outcomes are micro level. Yeah, very basic micro level, just two, yeah. Like Boltzmann had a very, he studied gases, and he showed that the temperature of the gas is as macrostate closely connected to the moving energy of the single molecules. And there are 10 to the potence, or how is it? Hoch, yeah, 23. So that is an immense number. So, but this in macro, in the examples of Boltzmann, there were high numbers, and now in this situation we have very small numbers, just two. And the difference is, there are, in fact, there are. So if you look here, you see that the bit is closed. The bit is, that's the idea, that the bit is closed. You can have several bits, but the bit itself is closed. It's just one or the other. And even it does not say what they mean. The meaning of the bit comes from outside. With the distinction, it's very much different. We have the inside, the continence, yeah, the inside and the outside. But the outside is unlimited. If I make a distinction, I don't know what is else possible. Yeah. If I talk about houses and different kind of houses, I don't talk about dogs or horses or zebras or other things like distinction or food or anything else. I will manage. Okay. So we have the borders. Distinction have open borders. The bit is closed. And this is helpful for technical reasons. If you as a technician, you have to build machines. And if the machines are open, they don't work. I mean, open in their functions. They have input and output, but inside, their work is closed. So with the bit as a program. And the information content is also different, because the bit is, the information content, entropy is by definition one bit. Just choice of two possibilities. With a distinction, because this is much bigger, the possibility on the outside, the calculation of the entropy is such that one bit is only one bit if both are equally probable. If they are not equiprobable, the information is higher. If I have 100 elements or objects and I choose one, it is much more information than if I have two. That's the reason why the distinction is always higher than one, like entropy. The action is also different, and the distinction is important in my view to have context. The choice here is just by two, so it has no border. I just want to mention Mackay. I don't know if you heard about him. He's a British a pioneer of informatics who worked in the Second World War with radar detection. So detection is also the same thing we talk about now. And he distinguishes between the descriptive information content and the selective. And the selective is, of course, the bit, it's the choice. And the descriptive has much to do with the surroundings. Which signals he looks at. It's just what I do if I look at something. We have closed systems that we can construct with bits, and we have open systems that we cannot. Or we cannot completely. We try, of course. So I'll give you examples. The classification, most classifications are only hierarchical. It's a closed thing. The natural numbers, it's a closed set, even if it's unendlich. It is closed. The natural numbers cannot be pi, cannot be natural, is not a natural number. So it is closed. You cannot go out. The syllogism is a logic system, ancient logic system of the Greeks, of Aristotle, are closed. And these two, this is the first order logic, this is first order, second order, third order logic, that is used very much in my field, is useless. It's useless to really cover the reality. It's a closed system. If you have experiments in a laboratory, you try just to eliminate all the outside influences. And it is very costly sometimes. Like the Large Hadron Collider, you have to, that is the job, you have to cool down so no infrared beams come into this, because it would just destroy what you look at. Standards also, they are militant even, that no other things count. But what interests me are open systems, like biotope, society is open, human knowledge is open, languages, my job, are open. Brains, of course, are open. We have eyes, ears. We can move. We can move. I can move my fingers. I can act on it's an open system. Art, if art is not open, it's useless. Life, qubits. Qubits are now very much in discussion too. They have a problem because technically you have to isolate the quantum bits, otherwise it doesn't work. But it's very costly and it's nearly impossible. That's the question is because the qubits are open system, so we have to isolate them. And what I propagate is a dynamic logic, because if the logic is static, it is easy to reconstruct it in a machine. But if you want to analyze what is going on, you have to accept that things are dynamic. That is another project of mine. We started, this is the context of bit and form. It is too small to see. It's not intended to see. It's just to give you an impression how we work. And this is a diagram of forces of ideas. And it has very few types. It is a graph with types and relations. And this indicates a certain kind of relation as this one, as this one. This one means a contradiction. And contradiction is like a battery in my head. If there is a contradiction, I have to think about that. So if there is a contradiction, it moves. Yeah. And time is very important. So I don't talk about time now, but it would be over time. But I talk about entropy has to do with time. Re-entry has to do with time. And oscillation has to do with time. And auto persistent has to do with time. We finished now. Yeah, but this is what we're doing now. Yeah. If somebody is interested, this is my homepage, and this is the page for this kind of systems.
All right. Thank you very much.
Yeah.
Thank you. All right. Questions? Yeah.
Hey, my name is Adam. I very much liked your presentation.
Thank you.
I have a suggestion. Do you think that what you called open and closed systems is the same thing as what physicists would call reversible and irreversible processes?
Yeah.
Yeah?
Yeah.
Okay. Cool.
Exactly.
Now we're on the same page.
Yeah. That is, the chaos theory, like Prigozhin, he talked about this. And yes, I don't talk about now these things, but yes.
Yeah. So hi, it's Tim. Thank you very much. Very beautiful. Who draws the distinction? That is really a key question, seems to me. I tried to address it in my talk as well. When I pointed to the drive theory within Freud's conception, because and you put like right in the middle of your diagram here, energy. And could we think of it as kind of transformation processes of energy?
In thermodynamics, entropy means energy means work inside, so the potential to work. And entropy, tropos, like Tropic of Cancer, means the moving or the change, yeah, or the fold in manifold. So it is just something changing. And in thermodynamics, it is about this kind of energy. But in information, it's maybe difficult to talk about energy. Yeah. It is just the information. But I'm not sure. Maybe you can also postulate some kind of energy. Yeah.
I wanted to point out that I think there's a kind of an opportunity between your work and chapter 11 of Laws of Form, because in chapter 11, it begins with re-entry forms which are quite comprehensible, and we can think of them not just in terms of something binary going through it, but in terms of a whole context going through it. But then he speaks of these rather marvelous area of designs of asynchronous structures, which he built in order to count. But those same structures could have full contexts going through them. You could let the observer really be inside those structures and try to understand what they really are, what their potential is. Our feeling is that the potential of those structures is quite much wider, much more enormous than what we have seen them do so far.
Yeah,
I think your work would help in that regard.
Thank you. Thank you. From my side, chapter 11 is like a gem. Yeah. Like a gem. And I really admire Spencer Brown for this. It's so good. Yeah. Yeah.
Okay, yeah, thanks again.
I want to say something.
Okay.
May I say something to Luke Hoffman? I also think this, also in chapter 11, you have the imaginary truth values. And I'm interested also in physics. I'm not a physicist, of course, but I study this as a layman. And the notion of imaginary and real that build together the complex world is very interesting. And the work with you with the plus and multiplication. Yeah, that is also come to this. So there's a lot of things to say, but I think we stop now. Thank you.
Okay, yeah, thanks a lot. So that takes us to our coffee.